Mastering deep learning. RNNs and LSTMs excel in NLP tasks because they're wired to mimic human thought patterns. Where do recurrent neural networks, RNNs, and long short-term memory, LSTMs, networks draw their strengths from that enable them to excel in natural language processing, NLP, tasks? Recurrent neural networks, RNNs, and long short-term memory, LSTM, networks have been particularly successful in natural language processing, NLP, tasks due to several inherent strengths. Sequence processing, RNNs are designed to handle sequential data, which is a fundamental characteristic of language. Unlike other neural networks that process fixed-size inputs, RNNs can process sequences of arbitrary length, making them well-suited for NLP tasks. This ability to process sequential data allows RNNs to capture contextual relationships and dependencies between elements in a sequence, which is crucial for understanding language. Modeling temporal dependencies, RNNs are capable of modeling temporal dependencies in sequential data, which is essential for capturing the relationships between elements in a sentence or paragraph. By maintaining a hidden state that captures information from previous time steps, RNNs can learn to recognize patterns and relationships that unfold over time. This ability to model temporal dependencies enables RNNs to learn complex contextual relationships, such as those found in language. Gradient flow and backpropagation through time. RNN's ability to backpropagate errors through time allows them to learn from sequential data efficiently. This process, known as backpropagation through time, BPTT, enables RNNs to adjust their weights and biases to minimize errors and improve their performance on sequential data. LSTM's solution to the vanishing gradient problem. One of the primary limitations of traditional RNNs is the vanishing gradient problem, which arises when gradients are backpropagated through time. The gradients may become smaller as they are multiplied by the weights at each time step, making it difficult for the network to learn long-term dependencies. LSTMs solve this problem by introducing memory cells that can store information for long periods. The cell state is modified through a series of gates, input gate, output gate, and forget gate, that control the flow of information into and out of the cell state. This architecture allows LSTMs to learn long-term dependencies more effectively. Capturing hierarchical representations, RNNs and LSTMs can capture hierarchical representations of language, which is essential for understanding the structure and nuance of language. By learning to recognize patterns at different scales, RNNs and LSTMs can capture the hierarchical relationships between words, phrases, sentences, and paragraphs. Ability to process variable length input. RNNs and LSTMs can process variable length input sequences, which is common in NLP tasks. This allows the network to focus on the relevant parts of the input sequence and ignore the irrelevant parts. Parameter sharing. RNNs and LSTMs share parameters across time steps, which reduces the number of parameters that need to be learned. This makes them more computationally efficient and scalable for large datasets. Parallelization. RNNs and LSTMs can be parallelized, which enables them to take advantage of modern computing architectures. This allows for faster processing of large datasets and enables the training of larger models. Suitability for NLP tasks. RNNs and LSTMs are well suited for NLP tasks such as language modeling, machine translation, sentence classification, and text generation. They can learn to recognize patterns and relationships in language data, enabling them to perform tasks such as language translation, sentiment analysis, and text summarization. In summary, RNNs and LSTMs draw their strengths from their ability to process sequential data, model temporal dependencies, and capture hierarchical representations of language. These strengths enable them to excel in NLP tasks, making them an essential component of many NLP systems.